Hey everyone, in this example I would like to remind you guys of the Riemann sum definition of definite integral and then use it to compute this integral, use the definition to compute this integral, this definite integral. So let's start by remembering what the Riemann sum definition says. It says that given a definite integral from a to b of a function f of x dx, the integral is computed. By the way, let's draw a picture over here so that we can see exactly what's happening. Right now we have a interval from a to b in the x direction, and we have a function. I'll draw the function as a positive function for this, just for the sake of the picture. So we have a function y equals f of x, and we want to compute the definite integral. Remember, the definite integral is the area of the region that is bounded between the curve and the x-axis, and then the vertical lines x equals a and x equals b. So we want to compute the area of this region that I've designated here. And the way that we do this is by, like I said, by Riemann sum. So this is then computed as the limit. I'm going to write the definition first and then we'll draw the picture over here. So the limit as n approaches infinity of the sum, I goes from 1 to capital N, of f of xi star times delta xi. And what is this? So what are xi star and delta xi? Well, the idea here is that we take the interval from A to B and we chop it up into pieces, and these pieces, I'll just chop it up into a few pieces. They can be of any size that you want. You can distribute these points in any way that you want, and the only rules are that the first point of the chopping, it's called a partition. So the first point of the partition, x sub 0, has to be the left endpoint, A, and the last one, so the nth one, has to be B, and in between they have to count up. So this goes x1, x2, etc. So you chop up your interval, so that's A, right? And then you chop it up so that these points are increasing. And it goes all the way up to x sub n equals b. And capital N here is the number of intervals, the number of sub-intervals that we've partitioned our original interval into. And then what we do is we have to now somehow approximate the height of the curve by some point, right? So what we do is you choose in each interval, you choose any test point. It's called a test point. I'll choose this one here, and then you just call this, say, x1 with a star. They can be the endpoint, so maybe x2 star is the right endpoint, x3 star might be in between here, but you choose these test points, and then you go up to the curve itself, and you plot their heights. And the heights of these are exactly the values f of xi, right? So the heights of these points. Now, finally, you use these points to create little rectangle approximations of your curve, right? So you've got these little rectangle approximations that go right through the height that you've determined. The heights of these rectangles are exactly the f of xi. The bases, though, the base values, so the lengths of the bases, these are delta xi. So delta xi is always equal to xi plus 1 minus xi. So the right endpoint minus the left endpoint. Okay? Or maybe I have this backwards the way I've written it here. Should be like this, actually. So delta x1 is x1 minus x0. Delta x2 is x2 minus x1. So this is the proper formula. So now what do you have? Well, these two form the area of the rectangles, right? Areas of the rectangles, and then you add all those up, but that's not going to give you the right answer, right? So this is now approximately, this is approximately the total area, but it's not going to be right because you've got some we overshot on a couple of these. We might undershoot on some of them, not get enough area. And so how do we fix that? Well, we call in the limits, right? We make this into a calculus problem. This is not really calculus yet. Chopping something up and drawing rectangles, that's not really calculus. I mean, it kind of is, but what makes this a calculus problem is this limit right here. So this limit then, as the number of subintervals approaches infinity, these rectangles get very skinny, and the total area of the sum of those rectangles approaches the area of the shape that you're actually looking at. Okay, now when we actually compute with this, we're not gonna allow ourselves the freedom, okay, to actually choose a random partition like this. We are going to choose a very specific partition And we're going to choose the one that uses right endpoints, actually. So the right endpoint rule. And so a couple things are going to be true for us. So we're always going to choose our xi with a star to just be xi. And I'll write another formula for that in a second, because we're also going to choose a evenly spaced partition so that our delta xi is really just delta x, and it's always going to be b minus a, the endpoints, divided by the number of boxes. So evenly spaced partition, b minus a over capital N. And likewise then, when we do the right endpoint rule, our xi will just be our left endpoint, a, plus I times delta x. So the number of steps times the length of the evenly spaced intervals. Okay, so these two, this is what we're always going to use. So at least in Calc 1, Calc 2, all right? So we're going to always use this choice when we compute, all right? Now, when I say compute, I mean actually computing a function like this. In a proof or in a theoretical argument, we might want to go back to this general definition, and we should never forget that the general definition exists, right? So don't forget that you're allowed to choose a general partition in general. All right, let's actually compute this integral then by using this choice of the Riemann sum, this choice of partition. So the first step, like I said here, is to write out the parts. So let's just write down the parts. So we have b is equal to 3, a is equal to 1. I'm just going to kind of write it out in terms of the integral, right? Our f of x is equal to x squared minus x. All right, so these are the key pieces that we need to work with. So once we have these written down, we can now write down our delta x. It's always b minus a over capital N. So in this case, 3 minus 1 over n, which is 2 over n. All right, and then we're going to use this right endpoint rule. So our xi is going to be what? A. I'll write out the formula. A plus I times delta x. So it's going to be 1 plus 2 over n times I. All right, but now that needs to get plugged into our function, because remember, in the Riemann sum, it's f of xi. It's not just xi, it's f of xi. So this xi has to go into our function. F of xi is then what? It's going to be 1 plus 2 over n times I squared. The function says to square it. Minus 1 plus 2 over n times I. And at this point, we are going to want to multiply this out, combine the like powers of I, and kind of simplify this as much as possible. So I'm going to do that now. So the first thing we need to do is multiply this. You need to distribute. This becomes 1 plus 4 over n I plus 4 over n squared, I squared, minus, over here, this one becomes, it stays the same, right? It's just 1 plus 2 over n I, but that whole thing is subtracted. And so we see that we have here a 1 minus 1. Those are gone. And then similarly, we have 4 over ni minus 2 over ni. That just leaves 2 of these, 2 over ni, right? So this then leaves us with 2 over n times I plus 4 over n squared times I squared. Okay, and so now this needs to go into our formula for the Riemann sum. So our integral from 1 to 3 of x squared minus x dx is equal to the limit as capital N approaches infinity of the sum. We're going to have to work with this sum first, and then we'll take the limit at the very end. The last step is to take the limit. And the sum is of this term that we simplified, so 2 over capital N I plus 4 over n squared I squared. But don't forget to then multiply by delta x. Remember, up here in our formula, it's f of xi star, f of xi for us, times delta x. So don't forget to multiply by another copy of delta x, and that's just 2 over n for us. All right, and like I said, we need to start by computing the sum, so simplifying the sum. And this sum can distribute, everything here is inside the sum. So all of this is inside the sum, but the sum only cares about the i's, right? It only cares about I. And so this thing can distribute, if we do it very carefully, to just the terms that have the i's. All right, and this can then be, by the way, you have to be very careful if there's a constant term in here as well. It has to add up the constants, but we don't have that here. So this becomes our limit as n approaches infinity of, how's this going to work? Well, now we've got 2 over n times 2 over n. So that's 4 over n squared. And then the sigma, the summation, x on the I. So sum I goes from 1 to capital N of I. Plus, now we have 8 over n cubed on this one, times the summation. I goes from 1 to n of I squared this time. All right, and now before we can take the limit, we have to get rid of these summations. So at this point, you just have to know what these equal. So these two, there's a few of them that you need to know. These two you definitely need to know. So I'm going to go over to the side. I'm going to write down some formulas that we need to know. So first of all, if you add up from 1 to n, if you just add up 1 plus 1 plus 1 plus 1 n times, here you get n. Okay, so there's a summation that you might need. We don't need it on this one, but you need to know it though. So sum from 1 to n of I. This is saying we want to add up 1 plus 2 plus 3 all the way up to capital N. And this one you, I hope, remember from Calc 1, hopefully you derive this, is equal to n times n plus 1 over 2. So that one we do need. And then the other one that we definitely need here is the sum of I squared. This one's 1 plus 4 plus 9 up to n squared, right? And this one, it turns out, is n times n plus 1 times 2n plus 1 all over 6. All right, that one you should have proved in Calc 1 by using an induction argument. It's probably the first time you used induction. So you need to know that one. And then finally, the last one that you need to know for sure is the sum of I cubed. I won't write all this out because it's getting jammed up here on the side. But this ends up being quantity, n times n plus 1 all over 2 quantity squared. So it's n squared times n plus 1 squared over 4. But this is a nice way to remember it because it looks a lot like the sum of the i's, right? So now the two that we need are these two, right? So we're going to replace these formulae by these formulae, okay? And we just plug them in over here. So now what we have, this is kind of off to the side, right? But the stuff, again, if you haven't seen this, so this looks new to you, make sure you take some time to understand this. But this now becomes the limit. N approaches infinity of, make these replacements, right? So 4 over n squared times n plus 1 over 2 plus 8 over n cubed times n plus 1 times 2n plus 1 all over 6. All right, and then now we're ready to take the limit. The limit only acts on the n's now, so the i's are gone. Once we get rid of the sigmas, the i's are gone, and this now becomes, let's write this out a little bit more. So we've got our 2 times the limit as n approaches infinity of, I'll multiply this out, n squared plus n over n squared, plus this is now 8 times 6, or sorry, 8 over 6 times the limit, n approaches infinity of, when you multiply this out, you end up with 2n cubed plus what? 3n squared plus n over, we took out the 6, right? So over n cubed. This n cubed is still there. All right, and now we evaluate these limits. So these are limits as n approaches infinity, and so as n approaches infinity, the leading coefficient rules. This is a leading coefficient test, right? So you compare the largest coefficients on the top and the bottom of the coefficients of the largest power. So the leading coefficients, make sure the powers are the same. Here it's 2 and 2, here it's 3 and 3, so they are the same. And then the ratio of the leading coefficients, that's what the limit equals. And so actually the math, the calculus, is not so hard as long as you're keeping track of everything that you're computing here. So this becomes 2 times 1, that limit is 1, plus 8 over 6 times, this ratio is 2. Right? So this is then 2 plus 8 over 3, or this is going to be 14 thirds. And so that's the value of the definite integral from 1 to 3, x squared minus x dx, done by Riemann sum. Let's smile for that one. That one was a fun one.